All right, so thank you all for having me. This is my first time with the Bella Vista group. I've been to a few meetings of the Benton County group, but home is Springdale with Paul and that club down there. And so it's an honor to present two of my passions, ham radio, which is recently new, and astronomy. And when you mix those two together, you get radio astronomy. And so what I want to do today is go over a little bit about what radio astronomy actually is. And then we'll talk a little bit about some different applications. So we'll talk about using radio astronomy to observe Jupiter. And then we'll also talk about observing the sun. And then I'll talk a little bit about meteor scatter. Now, a lot of you know what meteor scatter is from a ham radio perspective. This is a slightly different twist, and I'll talk about that and get to show you an actual example. As we go along, I will also have questions and answers at the end. So, but if there's any super urgent question, feel free to raise your hand. All right, so radio astronomy is relatively new. As an entire field, obviously, people have been looking at the stars since they first looked up. And astronomy has had a huge influence in people's lives, people's cultures for a very, very long time, even today. But radio astronomy is relatively new, and it started off in, and apologize here, some of the lights are a little bit washing some of this out. But starting in 1932, is really when radio astronomy first got started. And in detecting these radio waves, they started noticing that there were different signals that were not earthbound. And they started off by looking at radio frequencies actually from our own galaxy. And that's what they initially were detecting. But over time, we've detected a lot more and more things, and we've even found things that only emit radio waves that we can't see visually. And so this field has just grown in the, it's not even 100 years old yet, and the exponential growth of this field is just amazing. Now, for us, when we think about radio waves, we have certain frequencies or wavelengths that we normally associate. Really, in astronomy, radio astronomy covers any part of the electromagnetic spectrum except for the visible wavelengths. Okay, so you will get radio astronomy referred to even if it's looking at gamma, really short wavelength gamma radiation. So oftentimes we associate radio astronomy with huge radio antennas. So we have an image down here of the Very Large Array, which is a whole set of gigantic radio antennas in New Mexico. Have any of you had an opportunity to see those? Oh, excellent, a couple of you. They're just massive. I can't represent the size of it in words. It's just an amazing sight. And so with these telescopes, what's that now? You've flown over it. Okay, yeah. So no, that's all right. That's all right.
How big is one of those things? There's no reference in the picture. So
that's true. And I'm not exactly sure how.
Is it 10 feet tall? Or
oh no, this is 100 feet tall easily. The massive nature of them, their motors are just massive, and they move extremely, extremely slowly. Their control mechanisms, they're actually on rail tracks, and they can actually move and change the configuration of them. But they are huge. They're hundreds of feet in diameter. Yeah, not your backyard type of equipment. But the point of that is that we say often uses radio antennas, but you can also do radio astronomy with very small homegrown projects as well. We'll talk about a couple of those as we go along. So we also use this process called interferometry. And what it does is, so how many of you remember from maybe high school of calculating the sides of a triangle? Okay, right? So one of the things that we try to do in radio astronomy is to measure the size of an object or a distance to the object by measuring it from different locations. Now, sometimes we can use something like this array where we can line up those telescopes and detect the subtle differences from the telescope on the right end to the telescope on the left end. But we can also use the Earth's orbit. Okay, and we can take the Earth at one point, and when it's on the complete other side of the Earth, and then you can get a measure of the distance because we know how far we are away from the sun, and you can draw a triangle to that. So we use that process to understand the distances to things, and then we also we can also look at very, very faint objects. Astronomical objects emit all sorts of light, not just visible light. X-rays, gamma rays, infrared heat, as well as radio waves and very long wavelength. And so there's a lot of different information that we can derive about these objects that's related to the wavelengths that they're giving off. Okay, and so radio astronomy is super important to our understanding of the universe and the whole field of astronomy as well. So there's some very specific frequencies that radio astronomy uses, and here are some of the common ones. And I apologize, it's a little bit small for the distance, but I'll read off some of these for you. But some of them are actually protected. So for example, one of them here is 70 centimeters that we're all familiar with. But that's also used in radio astronomy. One of them here is actually water vapor here. So over here we've got 1.2 centimeters. That's water vapor. And I point that one out. That's really important because when we are actually trying to get radio information, radio waves at that wavelength, our atmosphere blocks it from us because the water vapor in our atmosphere will absorb it, so we can't actually see it. So that's where we have to rely on having space telescopes that can detect our radio frequencies. So radio telescopes out in the sky, they get outside of our atmosphere, and now they can see some of these wavelengths that are blocked by our atmosphere. But there are plenty more. Maybe one of the most important is the 21 centimeter hydrogen wavelength. So this is a wavelength of light, of the electromagnetic spectrum, that's given off when a hydrogen atom has its electron really in an excited state, and it goes back down to normal, and it gives off that wavelength. Here's an example of this is actually looking at formaldehyde, an object out in space that has formaldehyde. Oh, we're all familiar with formaldehyde, right? You've heard about it at least. And this is the mapping of the object at those different frequencies. That's the kind of detail that we can get from radio telescopes. Here's an example where they've changed the different wavelengths that they're pulling at different frequencies at, and mixing these images together with red, blue, and green, and they can see different detail. So here you see a bit more detail in the blue. Compared to here, you see a lot of the detail in the actual arms itself. And that's a real great advantage that we can do with radio telescopes. It's a lot harder to do with the visible spectrum. And we do try to use filters and things like that in the visible spectrum, but it's much harder to do this kind of work. So let's talk about a couple of examples. So the first one is Jupiter. Jupiter as you all know, the largest planet in our solar system. It's a very active radio object. It gives out all kinds of radio waves. And there's a lot of neat information we can find out and study Jupiter by looking at radio waves. So there's really two main sources of radio waves from Jupiter. So the first one is caused by Jupiter having a super strong magnetic field. Okay? And that magnetic field traps gas and plasma that come from the sun. And from a process we don't understand yet, somehow that gets gathered at its northern atmosphere. And that plasma interacts with the atmosphere and discharges and gives off radio waves. The second process is actually from Jupiter's moon Io. How many of you have heard of Io before? Okay, good, a lot of you. So Io is the closest large moon to Jupiter. It's one of the Galilean moons. If you were to look at Jupiter through binoculars, you can actually see Io as well. Io is maybe the most volcanic object in our solar system. It has tons of volcanoes, and it's so close to Jupiter that Jupiter's gravity heats up its interior, and so it's always shooting out lava, and it even shoots out lava so much that it escapes from the planet. Because the planet's not huge, or the moon, I mean. The moon is not huge, it doesn't have a lot of gravity, so it's pretty easy for that to escape, and it just kind of forms this ring around Jupiter. And that ring causes, between Io and Jupiter, to act like a battery. And it's a 1 trillion watt battery, essentially. There's a voltage difference between them. And what happened is discharges happen, and it creates this plasma cloud, and this is what Jupiter looks like through radio in these two pictures here. These are two different wavelengths, and Jupiter's in the center, and you can see these lobes way out here. That's that gas that comes off of Io, and the radio waves that are given off by that plasma. So it looks totally different than a visual picture here. But this is actually a picture that I've taken through my optical telescope. Looks completely different. And I don't know if we'll be able to hear this because from a setup, but you can also go to YouTube and you can listen to the sounds of radio signals from Jupiter. And they're kind of creepy. Let's see if... So these are called L bursts. And then these are called S bursts. And this is converting them from, this converts it from the radio waves to sound. So this is my goal for my backyard project, just to be able to get some of these sounds out of it. Now, on YouTube, because we've visited Jupiter with spacecraft that also have radio antennas, there are even creepier sounds than that on YouTube that we've picked up from Voyager 2 and some other spacecraft. So I didn't put these in here, but if you get a chance and you get on YouTube, just look up radio signals from Jupiter, and Saturn also is is really interesting as well. So I highly recommend that. So one great thing for Jupiter research was a project that NASA funded that's called Radio Jove. And the whole goal of it was to get younger folks involved in astronomy and specifically in radio astronomy. And what NASA did was they came up with a kit that you could put together from scratch, or you could cheat and buy it already put together. But the idea for high schoolers, junior high, even some colleges, was to get kids interested and build these kits, a radio receiver. It has filters in it, so it's only looking at some specific frequencies, about 23 megahertz. And and you set it up with a dipole, and you can receive radio transmissions from Jupiter. And the idea was that ham clubs could could work with high schools and things like that. Now, the program's still around, but it's not quite as popular as it was in the late 90s, early 2000s. But it's still out there. You can still order the kits, and the program is still active. But the goal was to get these kids involved in astronomy, get them working on an electronics project, and then share results. And NASA created an online forum where they could share results and all of that. I'm not sure if that is still active. I've not been able to find any recent posts on that. But that was the whole idea behind Radio Jove. And here's what it looks like, just a pretty simple box that they could completely put together. A dual dipole. These are about 23 foot long dipole, and because they're for a specific, about 20 megahertz signal. They're phased so that so the phases would line up, and you hook that into the receiver, and you get signals like this up here off of Jupiter. And so that's a little bit about Jupiter. The sun is also a radio source that we can study, and it's currently the project that I'm in the middle of working on, but I don't have any results yet. Things have been too crazy, unfortunately, but I'm getting there. But the sun is the brightest radio source in the sky for us because it's the closest and biggest. Jupiter can actually even be a little bit brighter than the sun. But as you all know, there are very powerful processes, nuclear fission, going on inside of the sun. And that gives off all manner of radio waves. There are sunspots. There are very intense magnetic loops. How many of you have seen the prominences or the loops in pictures of the sun before? Good, a lot of you. Yeah, those are magnetic fields on the sun. And a lot of times that gas, that plasma, is funneled up through those, and that's where you see those prominences in solar storms. And those all give off radio waves. Different hot and cold spots you can see on the sun. The surface detail of what's called the chromosphere you can see on the radio wavelengths. And if you were to look at the sun, and this picture doesn't represent it, but if you were to look at the sun, it actually, from a radio perspective, looks much larger than the actual visible sun. And the reason for that is that the solar atmosphere is super hot. And when gas gets super hot, its electrons get stripped off. That's called a plasma. I've talked about plasma a lot, right? And when those electrons reattach, it gives off different wavelengths of light. And so the radio sun is much, much bigger because of what's going on in the atmosphere of the sun. And so there's a lot of different types of radio emissions for the sun. Some of them are, and I don't necessarily need to go through all of them here, some of them are related to flares and other kinds of solar activity, like type 4 here. Some of them are just due to small bursts and explosions that are happening in the sun. Some of them happen only for a few minutes, some for only a few seconds. Some of them can last for 3 or 4 days. It depends on the event that's driving it. But all of these can be received by radio astronomy. So what do you need to have to observe the sun? Well, you need to have a VHF receiver. You need to have a dipole or a Yagi antenna. You need to have a, what do I have here? Sorry, here. Oh, yeah, it's AM modulation. And you may need a preamplifier depending upon what frequencies you're looking at. So here's an example of someone that caught a solar ejection here that happened using a setup like this. You can absolutely, from your backyard with equipment that's easy to get hold of, build your own little radio telescope and see these things from the sun or from Jupiter even. So an example of this, and this is the project that I'm currently working on, this is called the Itty Bitty Radio Telescope Project. And instead of having a couple 100-foot wide dish, we use a DirecTV or dish, satellite dish. And basically what you do is you take that dish and you hook it up to a satellite receiver. Now this is really inexpensive. So my satellite dish, I didn't pull the one down from my house, but I saw one at a garage sale and I got one for $5. Online, I got a $15 satellite detector. And so you then hook it up with some phantom power going to your satellite dish, and you can actually open up the satellite detector, and you can do things like normally some of them just have a needle, some of them have a buzzer, right? So you can go in and do some things like go in and do some little modifications so the voltage that's driving the needle, let's say, instead turns into something that you can plug into your serial port of your computer and read the voltages off of your serial port. Or, some of them have buzzers that you can just turn that into the line in of your computer, for example, and record the audio directly of the buzzing. So there's different things like that to try to get the signal strength of the sun or from Jupiter for these. So I currently have my dish and I've got my satellite receiver. I've got it torn apart, but I don't have it completely all wired up yet. So that is definitely an in-progress project. So my hope is that by winter time I'll be able to have this up and going. But things are just a bit crazy. Things quiet down for us in the astronomy club come winter because we don't have as many outreach events. So that means more time at home to work on projects versus being out at, let's say, Hobbs State Park or at some schools and things like that and showing people things through telescopes or giving talks. So I'm looking forward to winter time to get to work on some project work. So last thing I want to talk about is a project that I worked on in August. So there's a very famous meteor shower in August called the Perseids. How many of you have seen the Perseid meteor shower before? Oh, great, lots of you have. Well, you probably know this year we were completely clouded out. And so I got thinking, and I looked up some things on YouTube and stuff, and I realized that on YouTube that there are some videos showing how we can use Meteor Scatter to actually detect meteors. Now normally, as hams, we think about Meteor Scatter as catching someone else's communication that's bouncing off of meteors, right? Well, this is a completely different twist. What we're doing here, what I did on Sunday the 12th or 13th was actually detect the meteors, okay, by capturing a signal that bounced off of it. Now to do that, I had to have a continuous signal. So what I used was the digital TV carrier signal for, I think, channel 3, I think it was. And I went an offset of that, and I monitored an offset. So my setup was a CB or 10 meter antenna, just one of those CB antennas that I happen to have going around. I hooked it into an SDR play. If those of you that are familiar with software-defined radio boxes, I have one of those, the RSP1, and I plugged it into my computer. And I used HDSDR, and what I got was this. I was monitoring this, and let's see if this will let me play it here. Is it playing? Nope. Come on, play. Let's see if I can make it play. No? Huh. Maybe it's taken a second. I'll sit here for just a second. But so one of the examples that you see here is the signal is actually off the edge of the screen. So I'm monitoring this area to try to find these types of signals. Is it going yet? Yeah, it's going now. So this is a signal, this is a bounce. And so the brighter it is and the longer it is, the more intense the meteor strike is. So who knows why? We'll start making this a little interactive. Any ideas as to why a brighter, longer signal would be a bigger meteor? Yes? More ions, that's right. So what do meteors do when they hit our atmosphere? Burn, that's right, they do. And when they burn, they leave behind an ionized trail. They leave behind a plasma, like I mentioned earlier, where the electrons are stripped off of the atoms, the nucleus of the atoms. It leaves a trail like that. The bigger the fireball, the longer it burns in our atmosphere, so the longer trail it is. So that's more time for that radio signal to bounce off of it. So who knows what it's called when the distance between where the radio, the reflected signal shows up and the primary signal? Doppler, good, Doppler shift, yep, very good, you guys are awesome. And so if I don't know if I can fast forward this or anything, but eventually what you start seeing are more of these coming through. Let me see if I can, I don't know if I can do this or not. And so I watched this for about 2 hours. I actually streamed it live on Facebook. There's actually still a recording of it out there on Facebook that you can go see it. And I got to see a whole bunch of meteors that I normally wouldn't have gotten to see with a really simple setup. It didn't even have a dipole. And I just sat my antenna just like kind of on my roof, on my gutter. So it wasn't really a sexy setup at all, but it absolutely worked for me.
A question.
Yes?
You said you were using the Channel 3 television signal?
Yep, digital.
So obviously you're not sending that signal.
I'm not.
So they were sending the signal and you just happened to, I'll use that.
Right.
So
And
it goes in the air, so.
And thankfully, I had some other people on YouTube do some research for me. It's a 55.280 or something like that megahertz is the digital signal, or maybe that's the offset. But so there's a specific, each of the digital stations have a carrier signal, and it's a continuous stream. And so I don't have to worry about things like if I were trying to detect a Doppler shift of, let's say, you and I, or off of a repeater, as you know, it's not a continuous stream of radio signal. So you could miss meteors because they zipped by when there was no communication going, no radio signals to bounce off. That's why I was looking for a continuous signal.
Okay, so you're just watching for the reflection.
Just watching for the reflection, that's it. That's it. And no more have popped up yet. But as it got a little bit later, the frequency increased too, which is what we actually see observationally when you're looking at meteors. You don't want to go out like at 9 o'clock at night because you won't see very many, but the later you get, 11 o'clock, midnight, even after midnight, you see more meteors. And that's because of how the Earth is turning and how it's interacting with the meteor streams. Who knows where meteor showers like Perseids come from? Anybody? Comets, yes. The leftover debris of comets as they pass through our area. So there are a handful of comets that intersect with Earth's orbit, and they leave behind this debris trail, and that's what we pick up in the atmosphere. There's in any meteor storm, there's so many that you can't even see visually because they're so small. They don't create that that lit up, the burning as you describe it in the atmosphere, but the radio signals can pick them up.
All right, another dumb question.
No, it's not dumb.
So some of these meteor showers are recurring like on a yearly basis.
That's right.
So the Earth goes around the sun once a year. So is that trail there all the time and the Earth happens to pass through it?
Yes, that's correct. Now, some things are, we're off by a little bit, right? So the Earth can pass through slightly differently, just minutely differently. So that's why year from year you can get superstorms, and sometimes you get, fuddy-duddies in terms of meteor showers. It changes a little bit year from year. NASA tries to predict some of those, and there are researchers who are trying to understand where it's more dense in the debris field of the comet and not. Usually the meteor storms are most active after the comet comes back around again. And so there's going to be a comet that's going to be coming here in December. I think December 16th is when it's going to be its brightest. We're predicting that I shouldn't say we, because I'm not predicting, they are predicting that this is going to be a comet that we're going to be able to see with the naked eye at night. It's going to be very bright. So it's going to be a great time this December. So pay attention. The news hasn't quite picked up on it yet. You know, the news likes to publicize special astronomical events. They're not quite there. They're focused obviously on a lot of other things. But once we get into December, it's going to hit their radar, and there's going to be a lot of publicity about the comet. And so that comet's going to refresh its own debris field, and you know, that associated meteor storm is going to get refreshed, if you will, replenished. So that's a great question. Any other questions? Have we seen any more meteors? I don't see any more meteors coming up there. I promise you that there's a bunch, but just when I first turned this on, there weren't a whole lot right at first. But let's do some other questions that you all may have.
Were you able to correlate any of the radio meteors with optical?
No, because it was cloudy. Yeah, and so that would be really interesting to do. And I actually have a thing that's called an all-sky camera that I can put in. My suspicion, though, is a lot of the little ones that I picked up, we probably would not be able to see. We got one coming? Yeah, here comes one. Good. Wouldn't be able to see visually because it's probably very small. Yeah, question up here.
Earlier you was talking about how it's just it's year-round, it's still there, but wouldn't it burn up or something in the atmosphere?
Well, so a lot of them do, but the comets leave a really wide tail, okay? And some of them only cross, some of them cross at different angles. So if you think about my arm here being the Earth's orbit, okay? And let me see how I can do this. All right. So here's the Earth's orbit, and a comet can come at a lot of different angles. The ones that come at angles where it's in our orbit for a long time leave a lot more material, and so those turn into the bigger meteor storms. The ones that kind of cut up through, they don't leave as much material, so they're the smaller storms, and some of those have probably gone away from comets way past. But some of these big ones, there's enough material to go year after year after year. Think about Halley's Comet. Have you heard of Halley? You probably haven't heard of Halley's Comet. When I was in college, Halley's Comet came around for a second time. And so Halley's Comet first appeared in 1910. The only reason I know this is that was the year my grandpa was born, and then my grandpa passed away in '86. Which is when Halley's Comet returned. So he's kind of like Samuel Clemens, I think it was. Mark Twain was born and died on the year of a comet, and so did my grandpa. But in 1986 was the last time Halley's Comet there. So that's 76 years. So that's 76 times that the Earth is going through the path of Halley's Comet, and it's eating up some of that material every time, but there's enough for it to, keep a meteor storm going. Now, not all comets create a meteor storm, just the ones that come really close to Earth's orbit. Yes?
How big are these particles that are left over?
They're anything from smaller than a grain of sand, to maybe dime-sized. There are not often anything that would be like the size of a basketball, not from comets anyway. They're all really small. Any other questions? Yeah.
Have you been out to the VLA?
I have not yet. That is my goal. This past summer, my wife went very near it. She took the kid. I couldn't go on vacation with them. They went out west and went not very far away, but they did go to the Lowell Observatory. But that is one of my goals, to get to VLA and some of the other sites out there. So it's, huh? Very large array. Very large array.
That's all remoted to another building.
Yes.
There's nothing at the site except a small transmitter.
Yep, that's right. Yeah, and It's amazing, just the tracks, the massive size of those things, and it's just amazing. And to have to coordinate all of them, I can't remember how, is it 23? I don't know, there's a good number of them that they all have to get them precisely pointed. It's a fascinating amount of engineering. Fascinating. All right, any other questions? All right. If not, thank you very much for, oh yeah, okay, one quick.
Just when they're creating the image from the radio transmission, when I think of a radio transmission, I don't see it as an image, right? Like with an XY coordinate. How do they do that with, like, let's say Jupiter?
Yeah,
right?
so they map false colors. So what they actually do is take different wavelengths and they say, we're going to make this red, and we're going to make these wavelengths, and sometimes it's just a fraction of wavelengths too, depending upon if they're doing what they call narrow band, which is looking at a very small set of wavelengths or frequencies, or if they have a wider band. What they do is they'll pick and map certain frequencies to certain colors. So what you get is a false color image. It's kind of like if you were looking at everything in infrared, you'd only see red, because you have to map them into false colors. How many of you seen thermal cameras before? Yeah, okay. So thermal cameras do the same thing. They map an intensity of these little wavelengths to either different shades of gray or different colors, and those are a false color image. But that's how NASA does it. And the galaxy that I showed you, I think it's M81, the galaxy that I showed you in the first couple of slides did that. And they changed the colors. If I can go back to it here real quick, I'll show you. It was an example where they changed the colors. Here it is, right here. They changed colors of different frequencies from this image to this image to this image. And by doing that, they brought out different details. And so depending upon what they're researching and what they're looking at, they'll do that kind of false color mapping. Or sometimes maybe they'll do no color at all, like this one here. It depends on what their point is, yes.
But they're actually mapping the location of those intensities.
Correct.
In XY coordinates.
Correct. This is no different than like a CCD on your camera that's capturing a certain part of the image that falls upon it with visible light. It's the same thing here. And some of these objects, by the way, they're scanning. So this may not be a complete image. It depends on the radio telescope that was used, etc. Sometimes they will scan and grab little pieces and then put that together as well. So there's a lot of post-processing done in radio astronomy, way more than traditional astrophotography, optical. So yeah, you're exactly right. Yes, Paul.
Speaking of traditional, can you give us an update on the telescope and how it's progressing and
Absolutely. So I'm president of Sugar Creek Astronomical Society. There's another astronomy group in Northwest Arkansas that's called NWA Space. And a lot of their members are also members of Sugar Creek Astronomical Society. NWA Space is a nonprofit with the goal of building a space and science center in Northwest Arkansas. So think Amazium, but for adults. And that's the goal, and have it be centered around science. So many of you may have read an article or seen a show about the super large telescope that NWA Space was able to acquire. And I apologize, I don't know all the details because I'm not a member of NWA Space, so I'm repping them as best as I can here. There was a college out in Ohio or Pennsylvania, western Pennsylvania, that had a refractor, meaning a telescope that has a glass on the front end, that was a 24-inch telescope. So its front lens was 2 feet wide. Okay, that telescope, they were going to redo this building where this old observatory was. It's over 100-year-old telescope. And so word got to the NWA Space group here, and they said, we want it. And they said, it's yours for free if you dismantle it and you transport it yourself. And so they got the funds together. They did this. The mount that the telescope sits on is tons and tons. It's super heavy. And so they brought the telescope here. They're in the process of consulting with how to restore the telescope. They actually want to use it as a telescope. And they are also pursuing funding to erect a building. The latest news is that the city of Lowell has granted them 20 acres out west of Atwoods, if you know where Atwoods is. And so they have a certain period of time now to get architectural plans drawn up, to get funding, break ground, and it's a multi-stage process, but things are moving forward. When you may have heard on the news that Mars was at its brightest recently, and it'll be at its brightest for like 40 years, we had a star party out there to raise money for the event. And so we were out there in the grass in this middle of this field with telescopes set up and everything, and cooked hot dogs, and we probably had 250 people there. So that's the update on the telescope. And just real quick, I'll give a quick plug for Sugar Creek Astronomical Society. We're based in Northwest Arkansas. We have a lot of members here in Bella Vista. We do a lot of public outreach events. You don't have to know anything about astronomy. You don't have to own a telescope. Just if you're excited about space, we would love to have you. We have public outreach events. Probably we're most famously known for having star parties out at Hobbs State Park every other year. November 10th will be our last one of this year, and then we'll start up again in February. During the summer, it's not uncommon for us to have 200, 300. I think our largest, we had over 400 people there. Come for a lecture, and then we set up our telescopes for people to look at whatever we want to point at, the moon, planets, nebula, galaxies, all of that kind of stuff. So if you're not interested in joining the club, but if look out for our Facebook page. We'd love to have you out looking through telescopes and seeing some great things out in the sky. So with that, I will thank everybody. I really appreciate the opportunity to come talk to you, and hope you enjoyed it.